to leave the cationic acids till after. All right. So a section that I kind of skipped over with you was the section about cationic acids, which is section 3.5. So Bronsted-Lowry acidity, assessing the relative acidity of cationic acids. So if you remember in section 3.4 when we did areo, so section 3.4 was the areo section. What we were looking at then was the stability of conjugate bases. And from that, we could determine the relative acidity of uncharged acids. So we said the weaker the conjugate base, the stronger the acid, the stronger the base, the weaker the acid, right? So now what we're going to do is we're going to actually kind of flip it around. And instead of determining acidity and basicity looking at conjugate bases, we're going to look at their conjugate acids. And so it says here to compare the stability of cations. So if we have something with a positive charge, what we're going to focus on is going to be the first factor. So if we go back to the whole concept of areo, we're only going to look at atom when we're dealing with something that has a positive charge. So it says it's helpful for comparing cations that have their positive charges on different elements. So let's take a look at these two compounds. So we have the ammonium ion. So remember, this is an ammonium ion, and this is the hydronium ion. And each of them is the conjugate acid of ammonia and water, respectively. So if you take ammonia, NH3, and you add, we'll put plus H plus, and here we'll take water, plus H plus, and you get the hydronium and the ammonium. Okay, so which one of these is going to be better at stabilizing the positive charge? Well, if we use the concept of electronegativity, well, which one of these is going to be better at stabilizing a negative charge? We said that oxygen was better at stabilizing a negative charge because it is more electronegative. However, here, the one that's going to be better at stabilizing the positive charge is going to be the nitrogen. Right? This is going to be better at stabilizing the positive charge, and therefore it's going to be a weaker acid, right? This is going to be the weaker acid, and this is going to be the stronger acid. Remember, the concept is that the oxygen doesn't do as good a job at stabilizing the positive charge, and so it wants to shed or lose the proton. It wants to get rid of the proton. So there we go. So we use atom to distinguish between the relative acidity of these two cationic acids, the ammonium ion and the hydronium ion. Again, to repeat, whichever element is less electronegative is going to be better at stabilizing the positive charge, and therefore it's going to be more able to hang on onto the proton, and therefore it's going to be the weaker acid. And you can see that manifest in their pKa's. We see that the ammonium ion has a pK of 9.3, and the pK of hydronium is negative 1.7. Again, oxygen, more electronegative, therefore not as good at stabilizing positive charge. All right. So the conclusion is, if we have a weaker acid, well, the weaker acid is going to come from a stronger base, right? And the stronger acid is going to come from a weaker base. And so what's the conclusion is that ammonia is going to be a stronger base than water. It's not a strong base like hydroxide, but it is a stronger base. It's a better proton acceptor than water. And that's why amines and ammonia are going to be stronger bases, than water or alcohols, anything with an OH group on it. All right, except for a carboxylic acid, that's another kettle of fish. All right, well, there's another situation that I want you to be aware of too. And that is, what if you're comparing two cationic acids that both have the positive charge on the same element, right? We're still looking at areo, okay? So before we were comparing two elements that were different, nitrogen and oxygen. Now we're looking at two nitrogen atoms. So if we compare this alkyl ammonium ion to the aryl ammonium ion, which one is going to be the weaker acid? Which one is going to be the stronger acid? In this case, what we do is we look at their conjugate bases. So we draw the conjugate base of each one of these. Okay, so if we draw the conjugate base of the alkyl ammonium ion, we get an alkylamine. And if we draw the conjugate base of the aryl ammonium ion, we get an arylamine. So now what we do, it says in both structures, the positive charge is located on a nitrogen. Which one is more acidic? In a case like this, we look at their conjugate bases. So here's the conjugate base of the alkylamine. Here's the conjugate base of the arylamine. What do you notice about the two lone pairs? Could anybody tell me, if I highlight this lone pair in yellow and this lone pair in green, which one of those lone pairs is localized? There's only one of them that is localized. One of them is delocalized. Which one is localized? The one in yellow or the one in green? It's going to be the one in yellow, right? The one in yellow is localized. So localized. The one in green are delocalized because they can participate in resonance. I'm not going to draw all the resonance contributors, but you could draw a whole host of resonance contributors. So if we think about a base, right, remember that a base is a proton acceptor, okay? It's got to be able to grab a proton. So you've got to be able to take a proton, right, like that, or you've got to be able to take a proton like this. So which lone pair is going to be more available to grab a proton or to attack a proton? Well, the localized lone pair is going to be much more available to grab a proton or to attack a proton, and therefore it's going to be the stronger base because the lone pair is localized. So I'll put here localized, therefore stronger base because the lone pair is available to attack a proton, whereas the lone pair on the nitrogen of the arylamine is delocalized, so it's not as available. And we see that manifest in their pKa's. I don't think I have them. Yeah, I do have them written down here, so I'll just skip ahead. If we look at the pKa of the aryl ammonium ion, we see that this is the stronger acid. Well, why would that be? Because it comes from the weaker base, because the lone pair is delocalized. On the other hand, we get the weaker acid that comes from the stronger base because its lone pair is localized. So there you have it. That's really the lion's share of what you need to know from section 3.5, except for you should have an idea of the relative pKa's of ammonium ions and aryl ammonium ions. So if we have an ammonium ion has a pK of around 9. Any alkyl ammonium ion is going to have a pK in the same range, okay? So you see that it's 10 to 11. Well, that's pretty darn close to 9. So 9 to 11 is always going to get you where you want to go. And if you have an aryl ammonium ion, it's going to have a pK of around 5-ish, okay? Somewhere in that neighborhood. We see that 4.6 to 5.1, well, that's all close enough to 5. And if you back up to the other ones, you see it's 10.7 to 9.8. So again, it's close enough. 9 to 11 is good enough, or 10 to 11, whatever, you're going to get the right answer as long as you remember those two things. So to rehash, if we have the positive charge on two atoms of differing electronegativity, whichever one has the positive charge on the more electronegative element, that's going to be the stronger acid. And when it comes to alkyl ammonium ions and aryl ammonium ions, an aryl ammonium ion is going to be a stronger acid. Why? Because the lone pair is less available, right? Because it's delocalized. And that covers all of section 3.5. That's the whole thing. So now, there's one more thing, and I actually went over this with you in detail in chapter 1, so I'm not going to spend a lot of time on this. But if you're wondering, what about an amide? Is an amide a good base? The answer is no. Amides are horrible bases. Why? Because as we went over at the end of chapter 1, the nitrogen here is sp2 hybridized. And since that lone pair, meaning this lone pair is participating in resonance, it is not basic whatsoever. All right, so let's skip ahead and cover the last section, which deals with Lewis acids and bases. And I told you on the first slide, I think today, that a Lewis acid is an electron acceptor. And the way that my students remember that is acid, oops, where's my highlighter? An acid accepts electrons, so 2 vowels. And then if you have a Lewis base donates electrons. And so you have 2 consonants, and that's a good way to remember it. So acids under the Bronsted-Lowry definition also are considered Lewis acids and bases. It's just the reverse is not necessarily true. So if you have a Lewis acid, it might not necessarily be a Bronsted acid, but if you have a Bronsted acid, it's definitely a Lewis acid. So if we take a look at the example that I have shown here, you have water being protonated by HCl. Well, you can see that the water is a base because it's an H plus acceptor. And you can see the HCl is an acid because it's an H plus donor. Okay, so that would be Bronsted-Lowry, but it also fits the Lewis acid base definition. Why? Because you can see that the acid is accepting this pair of electrons. So the acid is an electron acceptor, right? And you can see that the base is donating that pair of electrons. So the base is the electron donor. All right, there you go. So base, electron pair donor, acid, electron pair acceptor. All righty, there we go. So with that in mind, some Lewis acid-base reactions, like I said, can't be classified according to Bronsted-Lowry. For example, if you look at this one here, you can see that there's no protons in boron trifluoride, and there's no proton being transferred. So it definitely doesn't fall under the umbrella of Bronsted-Lowry, but you can see that this one is an electron donor, and you can see that this molecule is an electron acceptor. And so based off of that, we know that this is a Lewis base, and this is a Lewis acid. And then we end up forming what we call a Lewis base adduct. And we're not going to worry a whole lot about adducts at the moment, but you should be able to identify formal charges if you do see an adduct like this. So let's take a look and see if we can solve a problem which deals with some Lewis acid-base chemistry. So let's just divide this up into two. So there's two questions on here, A and B. All right, so question 3.32. We see that we are forming a bond between the aluminum and the oxygen of the carbonyl. And so how do we draw the curved arrow for that? Well, we're going to start on the pair of electrons on the oxygen. We're going to form this bond, right? That gives the aluminum, since it has 3 valence electrons, it's going to have a formal charge of -1, and the oxygen has 3 bonds and 1 lone pair. Therefore, it has a formal charge of +1. So if I look at this, if I call this, 1 and I call this 2, which one of these is the Lewis acid? Would it be 1 or 2? Absolutely, right? This is my Lewis acid, and this one is donating electrons, so this is my Lewis base, absolutely. All right, let's try the other one. It's missing some lone pairs, though, so we'll pencil them in. You need 2 lone pairs on the carbonyl, a lone pair here, a lone pair here, and 2 lone pairs there. So you can see that you're protonating the carbonyl oxygen, and so this is going to attack the proton of the hydronium ion, and then you're going to break one of those bonds and put a lone pair on the oxygen. So which one is donating a pair of electrons? If I call this 3 and I call this 4, which one is donating a pair of electrons? Absolutely, right? So this is going to be my Lewis base, and this one is going to be my Lewis acid. But you can see that this one also falls under the umbrella of Bronsted-Lowry, doesn't it? Right, because this one here is a H plus. Sorry, did that hang up? Can you guys still hear me? I don't even know who that was. Okay, well, let me figure out if I can. There we go. That was easy. All right, can everybody see my screen? Sorry about that. Have I got the foggiest clue who that was? All right, let's keep going. So where was I? This is a Lewis, sorry, I'm talking about Bronsted-Lowry. This is a Bronsted-Lowry base because it's a proton acceptor. So Bronsted-Lowry base, and the hydronium is a Bronsted-Lowry acid because it's donating a proton. So you see that in the second one, it falls under the umbrella of Lewis and Bronsted-Lowry, but the first one only falls under the umbrella of Lewis because there's no proton being exchanged here whatsoever. And there you go, my friends. That's all of chapter 3. We've covered the whole kit and caboodle.